Okay, and so now we have the next speaker. It's Rebecca Patrias, and she will talk about web invariants for non-crossing partitions. Okay, please.
Yep, great, thank you. Thank you for being here. So as the last talk of the day, I'm going to keep this pretty accessible. So let me know if you have questions as we go. This is joint with Oliver Pachenik, who's at Waterloo, and Jessica Stryker at North Dakota State University. So I'm going to start with our motivation for why we started this project. All right, so there's a pretty well-known bijection between two-row standard Young tableau. So I see an example here on the left. So standard Young tableau means we include every number 1 through the number of boxes. Yeah, and then we have the bijection between that and non-crossing matchings or partitions with blocks of size 2, like we see on the right. There's an operation on Tableau called promotion. If I apply promotion over here to my Tableau, what it's going to do to the matching is just rotate that picture. So it'll shift all the labels by 1. And if there's another thing I can do to Tableau called evacuation, if I apply evacuation to the Tableau, it's going to just reflect the matching. So there's that nice bijection with two-row standard Young tableau. And we have the same thing for three-row standard Young tableau. So we have this bijection between three-row standard Young tableau. Instead of non-crossing matchings, we have SL3 webs on the right side. So we won't get into that too much. Here's a picture. My red square just indicates where my 1 is. And we have the same properties as before. So if I apply promotion to my Tableau on the left, it's going to just rotate the web on the right. If I apply evacuation to the Tableau on the left, it's going to reflect the web on the right. So one thing that's nice about this is it's telling you something about promotion of the Tableau. In particular, it's telling you about the order of promotion. If you know that promotion corresponds to rotation, then you have a lot of information about the order of promotion. So what I'm interested in general is kind of K-theory combinatorics. So I don't really want to look at standard Young tableau. I want to look at increasing tableau. So an increasing tableau just has strictly increasing rows and strictly increasing columns. I'm allowed to have repeats. You can see I have 2 2s here. That's all good as long as I'm strictly increasing in rows and columns. And these are what's known as a K-theoretic analog of standard Young tableau. So standard Young tableau are giving you information about cohomology of the Grassmannian. Increasing tableau can give us information about K-theory of the Grassmannian. We won't get into that, but that's like where my background is. We have a lot of the same tools with these increasing tableaux. So I have a K version of promotion and a K version of evacuation as well. If we start in our 2-row case, things look pretty good. We have a bijection between what's called packed 2-row increasing tableau. So packed just means if I have 1 and 10 as my biggest and smallest entry, I have everything in between. I'm not missing any numbers. So packed 2-row increasing tableau biject to non-crossing partitions with no singletons. In other words, these are non-crossing partitions with blocks of size at least 2. So no singletons, blocks of size at least 2. We have the same nice properties where promotion on the left corresponds to rotation on the right. Evacuation on the left corresponds to reflection on the right. So that all looks great for the 2-row case. However, if we move to 3 rows, we don't know anything. So we have no idea what, well, we have some ideas, but we don't really know what kind of objects we should biject to. Some kind of partition, non-crossing something. We don't really know what should go there. And why this is of interest is because there aren't results about the order of promotion for these 3-row increasing tableau. So the order of promotion for 3-row increasing is not something that's proven. It's an important case because once you get to 4 rows, things kind of go crazy. So 2 rows is super nice. 4 rows, everything explodes. And so 3 rows is this boundary case. And we really want to be able to figure out promotion on these 3-row increasing tableau. And so the idea is, well, if we could biject them to some kind of object like we've been doing in the other cases in such a way that promotion corresponds to rotation, then that's going to give us the information that we want about promotion on the increasing tableau. So this is what we really want to do. We tried to work on this for a while, just kind of guessing and hoping for the best, but it just didn't get us where we needed to be. So I think my next slide kind of just says that. So what we're going to do is take a step backwards. So in all of the previous cases, there's kind of this hidden piece where the objects on the right, the webs and the matchings, all have nice polynomials associated to them, nice invariant polynomials. But we don't know what those invariant polynomials should be for the increasing tableau. So for standard Young tableau, we have these nice invariant polynomials. Maybe if we figure out what the invariant polynomials for the 2-row case should be for increasing tableau, that would somehow help fill in the background that we need for us to figure out this question, which is what we want. So we want to figure out polynomials associated to those non-crossing partitions that we talked about. So again, that's kind of the motivation. Now I'll start with some background of that project. So we can consider this matrix of indeterminants and the set of polynomials in the variable set. So there's any polynomials in the variable set. So you could have like x1, y3 minus x3, y1. We can act on the left by SL2. So for example, here's an element of SL2. I'll do left multiplication. Here's my new matrix of variables. And I'll change my polynomial accordingly. So before I had an x1, now my x1 turns into x1 plus 2y1. And I'll do that for each of the variables in my polynomial. And that will give me the action, I guess. In this particular case, we can see that we ended up with the same polynomial that we started with. So this polynomial is invariant under the action. And we might ask, well, which polynomials are invariant under this action, which is, of course, very well known. So as an algebra, the algebra of invariant polynomials is generated by the set of 2x2 minors of our set of our matrix of variables. So just exactly like that example polynomial that we had. So I want to pick a 2x2 minor. That's going to be one of my generators. And I'll talk about that 2x2 minor by just telling you which 2 columns I want. So Pij will represent the minor with columns I and j. So those are our generators. Let's think about how we can represent these in different ways. So here I have a product of my 2x2 minors. And first I'm going to represent them with this arc diagram, just in the straightforward way. So I have a P1, 2. So I'll put an arc between 1 and 2. I have 2 instances of P3, 4. So I'll put 2 arcs between 3 and 4. So that's a super straightforward way that I can illustrate this product of minors. Alternatively, I could use this 2-row tableau. So again, straightforward. I have a P1, 2, so let me make a column with 1 and 2. I have 2 P3, 4s, so I'll make 2 columns with 3 and 4. Of course, I can order things how I like, so I can enforce the first row to be weakly increasing, but then I have no control over the second row. So I have kind of a semi-standard tableau. I don't know. So we can control the first row, but we have no control over the second row. So we have those two ways to encode the products of minors. Okay, so our 2x2 minors generate the set of invariant polynomials. We can encode an m-fold product using a 2-row tableau with weakly increasing first row. Okay. Standard monomial theory then tells us that the set of semi-standard tableau will give us a linear basis for the degree 2m homogeneous part. So if I just restrict myself to semi-standard tableau of the right size, that's going to give me a basis, a linear basis for this invariant set. So we're going to restrict our setting a little bit further, and we are going to say that we only want to use each column of the matrix once. So if I have a 14-column matrix, I'm going to end up with a product of 7 minors, right? I'm going to use each index exactly once, and I'm going to end up with something like this, and those are the products that I'm going to care about. So in that case, when we represent it as a tableau, of course, since we haven't repeated any of the indices, I'll now have a strictly increasing first row with still kind of a wild and uncontrolled second row. On the other side, I'll end up with a matching. In this particular picture, it's non-crossing, but in general, it might be crossing. So I'll get some kind of matching and some kind of tableau with a strictly increasing first row in this restricted setting. Okay, so then if we kind of put all the pieces together, it's not too surprising to see that in our restricted setting, the basis is going to be standard Young tableau. So we're going to have strictly increasing rows, strictly increasing columns, and the basis will be the non-crossing matchings. So for example, let's say my matrix M of variables has 4 columns. So I have these 3 different products of minors where I use each column exactly once. And then I've drawn below each product of minors the corresponding tableau and the corresponding matching. So I just want to show us here that these 2 bases are actually different bases. So if I look first at the tableau, I see my first tableau is a standard Young tableau. Great, I'm strictly increasing in rows and columns. My second tableau is standard. Great. My third tableau is not standard, so this is not a basis element. So my basis would be the first 2x2 tableau. If I'm looking at the matchings, my non-crossing matchings are the basis elements, so clearly my basis is the first and third matching. So we can see here that those 2 bases are different bases. Okay, so we have a standard Young tableau basis and a non-crossing matching basis. Let's focus on the non-crossing matching basis. So since our basis is non-crossing matchings, I should be able to take a crossing matching and represent it as a linear combination of non-crossing matchings. And we do this using kind of our normal uncrossing rule. So if I see a crossing, I can rewrite it as the sum of these 2 non-crossing pictures. Great. Okay, so let's take all of that and add a right action as well. So before we were acting on the left by SL2. Let's add a right SN action. So I'm going to act on the right by multiplication, which will permute now the columns of my matrix of variables. So here, if I act by the long cycle, I'm just permuting the columns of my matrix, and then I'm going to change my polynomial accordingly. So we have our friend P13 over here, just like before. X1 became Xn, so our X1 is becoming an Xn, etc. So we have this Sn action. All right, and this right action of Sn that permutes the columns in our restricted setting where we're just thinking about polynomials that use each column exactly once, this is giving us the spec module of shape MM. So what we have then is a basis for the spec module of non-crossing matchings and a basis for that spec module of standard Young tableau. Okay. In 3 rows, we have exactly the same story. So just take everything I did just before and do the same thing with the 3-row matrix of variables. I can act on the left by SL3. I can act on the right by SN. And I'm going to end up with a standard Young tableau basis and over here an SL3 web basis for the spec module of shape MMM. Okay. So let's take all of that background and kind of come back to what we're trying to do. So what we're trying to do is look at 2-row increasing tableau and matchings. Well, non-crossing matchings, but matchings. And we want to associate some kind of invariant polynomial over here in a similar way. So we want to take a matching and then find a polynomial for that that's meaningful in the ways that we want. So what are the things that we want to hold for those polynomials? Well, we want to be able to come up with them. So we want to be able to associate a polynomial to any, sorry, not matching. We just explained the matchings. To any partition with no singleton blocks. So any partition with block size at least 2, I want to associate a polynomial to that. I want this promotion to be rotation, evacuation to be reflection. So I want the long cycle to rotate the partitions. And I also want our project to agree with some previous work. So Brendan Rhodes had kind of diagrammatically done this before, and he had these crossing rules that you see down here. And so our goal in this project is to have our whole world agree with his up to sign. So we want our crossing rules and his crossing rules to be friends with each other, ideally. Okay. So before I get into the polynomials themselves, let's just look at these crossing rules. This is supposed to be a minus sign right here. And let's in particular look at, well, first let's notice that the number of blocks doesn't change. So in each crossing rule, I'm starting with 2 blocks crossing on the left, and I'm resolving it into a linear combination of things with 2 blocks. That's great. However, we need to notice that the block size itself does change. So if I look at the 3rd crossing rule down here, let's take each of those vertices to be a literal boundary vertex. So let's say this is 2 blocks of size 4. Then notice over there on the right, I'm getting a term that has a block of size 6 and a block of size 2. And that's the only block of size 6 that I see on the right. So that'll affect what we need to do later. The fact that those block sizes can change in that way. We'll come back to that in like 1 minute. Awesome. All right, so let's get into it. So here I have my partition with no singletons. And what I'm trying to do is associate a meaningful polynomial to this. So what's the most naive thing to do? Well, let's just exactly copy what we were doing before. So I have this arc 1, 4. So let me, I guess, kind of go through the tableau route. So I have the arc 1, 4. So let me make a tableau with column 1, 4. I have the arc 5, 7, 8, 9. So I'll make the column 5, 7, 8, 9, etc. And that's a naive first guess of what we can try. But we can see easily from those crossing rules that we just talked about that this won't work. Why won't this work? Well, if I think about the polynomial that I would get from this tableau, so what would I do? I would take, this would correspond to a minor with columns 1 and 4. And it has 2 variables, so we'll use rows 1 and 2 for that minor. This column here, I would take the minor with columns 2, 3, 6, and 10, and rows 1, 2, 3, and 4. Similarly, for that last column of my tableau, my minor would only involve rows 1 through 4. So the naive polynomial would only involve the first 4 rows of variables. Okay, but let's notice that I have here 2 blocks of size 4 that are crossing. And so I should be able to use my crossing rules from up here to uncross those 2 blocks. And what we see is when I uncross those 2 blocks, I'm going to end up with a block of size 6. So when we uncross the blocks of size 4, we end with a block of size 6. And using our naive guess for that polynomial, that block of size 6 is going to use the first 6 rows of variables. From our matrix of variables. Okay, and that's clearly not going to work. I can't take something on the left here that uses the first 4 rows and then set it equal to something that's going to use the first 6 rows. So our naive guess is not good enough. We're going to need to try something more complicated. And essentially what we're going to do is take this naive guess tableau and kind of stretch it out so that we don't need to worry about the block sizes changing. Okay, what is that going to look like? That's going to look like this. So we're calling these things jellyfish tableau. Same as before, the blocks are the columns. So again, I have 2, 3, 6, 10. So I'm going to have a column 2, 3, 6, 10. Each of these tableau has a column 2, 3, 6, 10. And same for each of the blocks of our partition. We're going to upwardly top justify the first 2 rows. So I'm always going to have the first 2 rows in a big block like this. And then I want to have exactly 1 entry in each row below. So we can see in each example, we have the top 2 rows are kind of filled up. And then we just spread out the rest of the column so that I have 1 entry in each row. So if I just top justified all these tableau, I would get our naive guess, but we're spreading them out vertically. We're calling these jellyfish tableau because we kind of thought like they look kind of jellyfishy. Okay, so what we're going to do is we're going to take our partition with no singletons and write down all of the jellyfish tableau that correspond to it. Okay, and each of these jellyfish tableaux are going to correspond to a minor or a product of minors. Okay, in this way. So I'm going to have some kind of inversion number out front that we won't worry about. I'm going to look at each column of the jellyfish tableau. The entries are going to tell me the columns of my matrix of variables that I use. So I'm going to take the minor with columns 2, 3, 6, 10. And then the rows that appear in that column in the tableau will tell me the rows of the matrix of variables that I use. So here, my tableau lives in rows 1, 2, 3, 4. So that's the contribution from the first column. My next column here in blue, we'll use columns 5, 7, 8, 9, and we'll use rows 1, 2, 5, and 6. And then lastly, I have a minor that use columns 1 and 4 and rows 1 and 2. So each of those jellyfish tableau will correspond to this product of minors, and then we'll just add them all together. So again, if I started with this partition with no singletons, I'll form each jellyfish tableau that I can. Each of those corresponds to a product of minors, add them together, and that is the polynomial that we want. So we're going to call that the invariant that we get for our partition. Okay, so our theorem says then that this is a basis for a spec module. So it does mirror the same stuff that we saw in that background section. So if I'm looking at non-crossing partitions with no singletons, it is giving me a basis for this spec module of shape DD and then a bunch of ones. Our long cycle acts by rotation, our W naught acts by reflection, all the properties that we wanted. So everything works out great. Just to show a nice picture, I guess, we not only agree with those former crossing rules up to sign, but we can generalize them. So we have a more general crossing rule shown in this picture. We won't focus on that too much. Okay, I'm calling them invariants, these polynomials, but what are they invariant under? So they're invariant under the left multiplication by the following subgroup of SLD. So I want to multiply by matrices of this form. Okay, so invariant polynomials, great. They form a basis of a spec module, great. So we finished this project and we thought, well, let's explore a little bit more with jellyfish tableau before we go back to our original question. So what we did is we just kind of allowed our jellyfish to be thicker. So for example, over here is a jellyfish tableau where we top justify the first 3 rows of our tableau. So here we would say R equals 3. And we're going to get these from partitions with block size at least 3. So before we had partitions with no singletons, so that's block size at least 2. That gave us jellyfish with the first 2 rows top justified. We're just going to allow that number to change. So here's an example for 3. It turns out if you generalize in this way, it's not quite so nice. So the associated polynomials that you would get are linearly independent inside of a certain spec module, but they don't span the spec module. So we no longer get a basis. We do have the nice property that the long cycle still acts by rotation of the partition and W naught acts by reflection. So I guess that's how it goes. All right, so now what we're going to do is go back to our original question, which is what we've started working on now. So we want to take what we've learned about the 2-row increasing tableau, along with what we know about the 2- and 3-row standard tableau, and try and morph these into one story and figure out what we need to do with a 3-row increasing tableau. So that was the motivation for this project, and that's what we're getting back to now. Also of interest, there's some recent work by Jesse Kim and Brendan Rhodes that's super related to what we're doing, but we haven't really sat down to figure out the explicit bridge to get from their work to our work. So that's something that should be done as well. Yeah, so that's all that I have to say. Thank you.
Okay, thanks a lot for your talk. Okay, Karin, do you have some question? No. Does anyone have a question or comment?
No, I do, but I think my I was muted.
Okay, yes, now we can hear you.
Okay, very good. Yeah, so I was wondering whether the basis that you get for all those spec modules can be used to somehow find some combinatorial descriptions of tensor product multiplicities for Sn. I mean, of course, that's a very difficult question in general.
Yeah, we haven't thought about that at all. So at this point, I don't know. We haven't. Yeah, we haven't thought about that.
Yeah, thank you.
Okay, there is another question by Ben.
Thank you for the talk. I was really struck by the fact that you wanted to match Rhodes non-crossing rules only up to sign. Why? So I don't know anything about Rhodes non-crossing rules, so I might just lack the context. But like, if you want to hit something like that, why wouldn't you want to hit it on the target? Like, what's the intuition behind that being the right thing to ask for? Does the question make sense?
Yeah, so the short answer to that question is that his signs are kind of weird. And they just, like in the diagrammatic setting, everything worked out fine, but we just weren't quite convinced that that's the way that it needed to be.
I see. So it wasn't like the sign convention that Rhodes is using was sufficiently canonical that you felt bound to it.
Yeah.
But yet you did feel bound to the supports.
Yeah.
Cool. Thanks.
Okay, are any further questions or comments? Okay, let's thank the speaker again. And let's thank the all speakers of all our 2 days of this workshop. I'm very happy that everybody managed to give a talk here. And I'm very grateful for your presence at this workshop. So we will put all your talks on our webpage. And so if you want, you can send us your slides. We will also put your slides on our website. But of course, you don't have to do it if you don't want it. So, okay. Okay, so thank you, everybody.